So hypergeometric distributions, got a little, this is just like a screenshot. It's not really going to help us a lot. I just thought it looked better than just having the words up there, to be honest with you. Alright, we're going to get right into a question, and then I'm going to kind of, maybe in a slide or two, I'm going to do maybe a more thorough job of explaining exactly what hypergeometric is. But let's get to this question right off the pot, because it kind of relates to what we just did earlier. You have the option of two types of tests tomorrow. The first option would be 30 multiple choice, each of which has 5 possible answers. The second is 50 true or false questions. Unfortunately, the teacher hasn't told you what's on the test, so you will simply have to guess. So essentially, you're guessing on every single question. Alright, so what percentage of the mark should you expect to get on each test? Now let's remember what expectation and expected value means. Expected, we just talked about this, number of questions, or and then the probability, right? The number of items in the probability. So if you're doing the multiple choice questions, you should expect, what kind of mark should you expect if you're just guessing? Well, what is your probability of getting a question right if there's 5 possible answers? Well, it's 1 out of 5. Because if you're just strictly guessing, you don't know, you're just guessing blindly, 1 out of 5 chance. Now, how many questions were there? Well, there was 30 multiple choice. So we're going to multiply those together, and we're going to end up with 6. That means you would get 6 correct if you're just purely guessing. And that would give you a mark, 6 out of 30, not very good, by the way, 20%. Okay, now, in the true-false questions, or the true-false test, okay, the expected value is going to be, again, how many questions you had, 50. And what's the probability of guessing it right? Well, you got a lot better odds, right? 1 out of 2 or 50-50. So you should get 25 right. So, as you probably would have guessed, I hope, that a true-false test versus a 5-question multiple choice, if you're just guessing, you have a much better chance to pass that true-false test. Now, how does that kind of play into what we did this morning and earlier today and what we're doing now? Well, both of these tests that we just talked about, the true, false, and the multiple choice, are examples of repeated independent trials. Because it doesn't matter if the first question was true, the second one could be true or false. Right? And in fact, I know some people who have made tests with like 10 straight false answers in a row just to mess with kids' heads. I would never do that, but I've heard of people doing that. However, the outcomes of consecutive trials can also occur in a dependent way. So we looked at independent with binomial distribution. Now let's look at dependent. In other words, suppose you're dealing cards from a deck. As you deal, the probability of each successive or next card will depend on what the previous card was. Right? As soon as I start dealing cards out, my probability of getting a certain card is now changing, because more cards are gone out of the deck. So it's definitely dependent on the previous activity. Whereas rolling the dice, right, if you're putting cards back in, replacing them, that's different. But rolling the dice is a perfect example, or flipping a coin where the previous thing has nothing to do with the second one. Whereas dealing cards, if you've ever played cards before, as you get lower and lower, the chance of having cards is less and less. So hypergeometric is when situations where the probability distribution involves a series of dependent trials, each of them with success or failure as the only possible outcome. So in other words, you can't have a tie. You can only success or fail. You can only win or lose. These types of distributions will involve combinations. So we just did combinations last unit, so that's really nice because that's pretty much most of hypergeometric is combinations, because the order doesn't matter. So, for example, we've got this little top hat upside down. We've got 20 names in it. 12 of those names are female. So obviously the other 8 are male. If 5 names are drawn from the hat, what is the probability that there are 2 female names drawn? Now remember, probability meaning we're going to have this fraction. We're going to have this fraction. But the bottom is the total outcomes. Well, the total outcomes, there's 20 names in my hat, and I'm choosing 5 of them. So this is very similar to some of the stuff we did last unit. Now, what's the probability of drawing 2 2 females. Well, there was 12 females, and we're going to choose 2 of them. But remember, there's also 8 males still there. And in this case, we have to choose how many more to get to 5. We need 3 more. And this is the one that I like to remember as, right, the first 2 numbers add up to here, and the second 2 add up to here. Again, we're going to round to 2 decimals, 0.2384. So roughly 24% chance that 2 females' names are drawn. Okay, let's continue on. Now, we've talked about this already, about expected, but let's talk about it again in terms of hypergeometric. So to find the expected value for a hypergeometric distribution, determine the proportion of the total and then multiply it by the number of trials. Now, truthfully, this is very similar. Expected value is almost always kind of the same. It's like the number of things times the percentage or chance it's happening. It's almost the same. It says proportion, but realistically, we know that as a fraction, which we'll kind of keep in mind as a percentage, or as a, pardon me, as a probability. So what is the expected number of women from the previous example? So my expected, my EX, is going to be the proportion of women in my hat times the number of trials. So the proportion of women, there was 12 women out of a possible 20. And the number of trials, well, we pulled 5 names. So we're going to multiply and divide and find out that the expected number is 3. So again, expected values, expected outcomes, it's all pretty similar stuff. Alright, let's look at another one here. A box contains 60, 5 dozen, heads of lettuce. There are 8, I'll just put that in there in case, 5 times 12, right? We're going to forget that. 60 heads of lettuce. There are 8 spoiled heads in this box. A person chooses a dozen at random. Okay, so now got all these numbers. We know that there was, in the box, there was 60 heads of lettuce. In that same box, 8 of them were bad. And that a person is now taking a dozen, which we know is 12. Okay, randomly. Let's find the probability. So we're going to break this up into 2, I think, A and B. What's the probability that they get none of these spoiled heads? So what's the probability? Now in this case, the spoiled lettuce would be my X, which means I don't want any of them. So again, it's probability. So there was 60, choose 12 as my total number of outcomes. This person is looking at none of the spoiled heads. So there was 8 of them, and they are going to choose none of them, which is nice, which is kind of lucky. And then you have to think about how many are left over. This is a 60, not a 68, I apologize. How many are left over? There's still 52 that weren't spoiled. And we're going to choose all 12 from those non-spoiled ones. Okay, let's get rid of that. Let's do the second one here. What is the probability that they get at least 1? So, for like the 10th time, when I do at least, if it's at least 1 especially, the indirect is probably the quickest method. So the probability that X is greater than or equal to 1 is going to be the probability of anything, which we know is 1.0, minus the probability of getting no spoiled heads, which we just happened to do in the previous question. So I don't need to write a fancy formula. I just need to take my percentage, my probability, as a decimal from the last question. Okay, I think pretty straightforward this one, this question, this example. Let's do one more. This is not a very long lesson. I was trying to give you lots of time to get your homework done. For example, a fishbowl contains 10 guppies and 8 goldfish. 4 of the fish are removed randomly. What is the probability that at least one of these fish is a guppy? Let's see how much room we have here. Whoop. Okay, so let's look at this in terms of a probability. Now again, there's that at least one, right? So greater than or equal to 1 is a guppy. And again, you guys know me, I like doing it this opposite indirect way. So I'm going to go probability, so it's 1 minus, which is total, minus the probability of none, right? No guppies, which we kind of did the same thing in the last one. So then we got to figure out then, using these numbers, the 10, the 8, 4, 5, whatever, we need to figure out how we're going to find the probability of getting 0 guppies. So we know our total. How many fish are there total? Well, there's 10 guppies and 8 goldfish. So there's 18 fish total. And we're choosing 4 of them, right? Because 4 fish were removed. Now, if 0 guppies were chosen, we had 10 to begin with. 10 choose 0. And the rest of them were goldfish, but out of those 8, you have to choose 4 of them. So again, we're going to simply grab our calculator. I would like to do this part first, and then 1 minus my answer, and it gives me 0.9771. Okay, question B, or the next question. If the same fishbowl also contained 3 angelfish, how many angelfish would you expect, there's that word again, to remove if you choose 5 fish at random? So expect, as soon as you see that, you're thinking this. You're thinking expected value, and you're going to simply multiply the proportion times the number of trials. Well, 5 fish were chosen. Now the question is, what's the proportion? So we know there's 3 angelfish. Now, how many fish total are there? Well, we had 18 fish, right? We had 10 guppies and 8 goldfish. That's 18, but we also added these 3 angelfish, so that's 21 fish all in all. So we're going to multiply the tops, right? Fraction, 15 over 21. Change that to a decimal, which is about 0.7143. Now, remember, these expected values, depending on the situation, this might not make sense. Like 0.7 doesn't make sense because it's asking you how many fish. So you'd say that you expect, and again, you go with the numbers that are around this, right? So you'd say 0 or 1 angelfish. Probably closer to 1, right? Because you'd round that, but you wouldn't say exactly 1. All right, I honestly think that might be it. That's so short that lesson was. Not too difficult. There's only, what, 3, 4 questions in the homework? No excuse why I can't get this all done in the next 45 minutes. Get everything done for the day and be ready for tomorrow's last lesson / task.